turbulent. What is that number of Reynolds number, and how is it determined? How can you say that this one is laminar? We have transition and then we have turbulent, and with that we can be able to tackle chapter number 1, which is types of fluid flows. The next chapter is momentum equation, and for momentum equation, this one we are going to deal with flow in enclosed. First of all, you are going to deal with flows in enclosed places. May it be cylindrical, maybe rectangular, triangular, in enclosed places. And we are going to determine either linearly, the momentum equation linearly, the momentum equation in angular, and we are going to calculate the amount of forces that hit the pipe, maybe, or that enclosed system. What is that amount of force that are used? The same way we are going to deal with jet propulsion, the amount of force that passed through a jet. What is that amount of force that passed through a jet? What amount of force do you need to hold that jet so that you can be able to resist that force that is moving through a jet? So in momentum equation, it involves two parts: application of linear and angular momentum equations and jet propulsion. And in application of linear and angular momentum equation, it's what will take the most part. Maybe this one you can do it within maybe 2 or 3 lectures, mostly 2, and we can be able to push ourselves. We do it with 1.5 so that we can be able to finish that second topic. On the third topic is steady flow between boundaries, and this one is all about applications. And you have different applications. That is, one is dashpots, and dashpot is like a shock. You see those telescopic pistons. It's like those telescopic pistons, or vehicle shocks and things like that. So that's the dashpot where it lies. That's what we call dashpots. And slider bearing, and we are going to deal with more applications because there are more applications in steady flow between solid boundaries. And the main thing that we are going to get through this, that most of the topics in fluid mechanics too, they are in between boundaries. Their calculations are in between boundaries. So that's what we are going to deal with most of the time. The other topic we are going to deal with is steady flow in pipes. Remember, here we had steady flow in solid boundaries. Now in pipes, solid boundaries, it can be in any shape. Now we are going to deal with steady flow in pipes, and we are going to calculate all those flows and how we can get maybe steady flow. Sometimes it can be turbulent, how you're going to get steady flows. Then the other topic is unsteady flows in closed pipelines. And here we are going to talk about maybe water hammers, surge tanks, shafts, surge controls, how you can be able to control the surges. And each and every example here, we are going to try and bring what it means in every way in this life, where the application in life, like water hammer. I think maybe when you are doing fluid mechanics one, I don't know if introduced to water hammer, but it's there. We can do experiment using water hammer. Surge tank, I will explain what it means with the diagrams and things like that. The other one is the other topic is power transmission through pipelines. And power transmission through pipelines, we are going to calculate if you have a transmission through pipelines. This is because if you get an opportunity to go maybe how that pressure through pipe, the power through pipeline works is because you are pumping maybe oil from Mombasa to Nairobi. You are not, some places you know to use gravitational force, but how are you going to have that power and being transmitted all through the system? So we are going to calculate that. Know all about the pipe networks, how you can be able to do pipe networks, what is the flow rate through the pipe networks. Maybe you go to places like, I give you the case in Nyeri, Nyawasco, how are they connected, all their pipes, so that they can be able to supply water? How are they connected? Have they connected their sewerage system so that they can be able to collect them down there in Kangemi? How have they done that? And with that, we'll be able to calculate the power transmission through pipelines and also do the pipe networks and see how we can be able to get all that. The other one is the chapter now. We are done with enclosed. Now we go to somewhere called flow in open channels. And flow in open channels, we are going to optimize. You see all those channels, channels that you see transporting water, may it be rainwater, which is very turbulent and varying, may it be those gutters on your, maybe kwa nyumba unaona those gutters and how they are. How can you be able to optimize? How can you be able to optimize these channels in irrigation schemes, especially in Moya? How can you be able, is a square channel better? Is a trapezoidal channel better? Is a semicircular channel better? How can we optimize these sections? Which one is better than the other? So in these, we are going to calculate all those channel calculation and see which channel is better than the other one, and try to get and maybe do a similarity between different types of cross sections. That is, mostly they will be trapezoidal, triangular, there will be the circular, and there will be rectangular, or the circle, or the square. So how are we going to calculate? How are we going to optimize all this? You can be told maybe the irrigation scheme, they want to build a channel. Is it to be trapezoidal, triangular, or rectangular, or circular? Which one is the optimum? So that now in the open channels, all those channels that move water, maybe from one section to the other, is it a stepping? Is it a gradually moving? You know, you want, because in open flow channels, we need the water to be moving using gravity. Are you using gradually flowing? Is it step flowing? Things like that. Is it rapidly flowing? What do you want? With that, we'll be able to calculate and see what you can be able to achieve from that. Then the last topic is dimensional analysis. And this, we need to do all the dimensional analysis, but the main thing is we are going to deal with dimensionless groups and similarity laws. So this, the main subtopic you are going to deal with is this. I know you have done dimensional analysis using dimensional groups, where you know this one is millimeter per this one is this and this, then you do the dimensional analysis. But here we are going to do dimensionless group, but using dimensional analysis theory. And here we understand the different types of theorems and how they are applied, and then we can be able to apply them, do the dimensional analysis and similarity laws. So that's all about fluid mechanics, and it will be a little bit heavy, but it's heavy due to calculations. You might seem that it's 55, but it will be more than that. This is because some topics in this, they don't have anything. They are just, especially here, the application, they just apply the application in Angular and they're done. So we are going to go deep in application in linear and Angular momentum equation, then understandable. So in our first topic, which is written here too, but it's supposed to be one, is types of flow, fluid flow. And there are a lot of types of fluid flow, a lot of them, but we only want to discuss the main ones. And the first one you're going to discuss is uniform flow. And in uniform flow, we have that this is a flow where velocity has the same magnitude and direction. This velocity is equal at every point in the flow, in the fluid. So at every point of this fluid, the magnitude and direction, every point is equal. So the magnitude and direction of the flow is equal. That's what we call a uniform flow. It might be an ideal, but it can be ideal. The reason is right now people are creating pipes that are non-stick in the inside. So they're using something called biomimic. They take the properties of maybe a leaf, arrowroot leaf. Arrowroot leaf doesn't, when it rains on top of it, the water doesn't stick on top of it. So they're using the biomimic technology. They go and mimic that surface, and that surface is put inside the pipe so that it doesn't stick. So that even if the water moves, even if there are collisions and things like that, the water doesn't stick. There is no a lot of collisions, just slides. So we can have the flow, uniform flow, which is flow velocity is equal in every point of the fluid, has got the same magnitude, the same direction. So hii haina bends. So in non-uniform flow, I'm telling you to discuss the main ones. In non-uniform flow is that at given instant, the velocity is not the same at every point of the flow. At any given instant, the velocity is not the same at every point of the flow. And this is what we have as every time. In every flow, we usually have this. This is because, as we had discussed in fluid mechanics 1, according to those boundary, if you have a flow inside the boundary, a lot of clinging to the surface. So the particles on the surfaces tend to have a reduction in velocity. Others, until you reach the center point where the maximum, you attain the maximum velocity. So most of the time is that. But we can have a uniform flow if the size and the shape of the cross-sectional area of the stream in the fluid. So remember also we have uniform flow, but in most cases in practice, you expect every practice that we have, most of them, you have non-uniform flow, where at any given instant, the velocity is not the same at every point in that flow. So in that flow, you expect different instances, different points, there is different velocity. You have steady, and in steady, the flow conditions. Now we are going to conditions. The conditions, and conditions, always put this in mind. The conditions, that is velocity, pressure, and cross-section area. Remember, the conditions are velocity, pressure, and cross-section area at any point do not change with time. Remember, the conditions at any point do not change with time. So when you have got steady flow, it's where at any point the velocity, the pressure, and cross-section area do not change with time. But in unsteady, At any point of the fluid, conditions change with time. The flow is described as unsteady. So these conditions, remember the condition are velocity, pressure, and cross-sectional area. They change with time. Always. But in when you have got maybe we don't change the cross-section area, we expect some variation in pressure and velocity, but also maybe cross-sectional area will not change. So if there is a very slight, maybe slight variation in velocity and pressure, and the average from one point to the other doesn't change a lot, then we call that flow steady. A slight variation, but the average I change from all those different points. The variation is too small, then we call it a steady flow. But if the conditions change in time from one point to the other, then we call it unsteady flow. So now we combine. Let's combine uniform, steady, non-uniform, steady, maybe non-uniform and steady, and see what it gives us. So when you start with the steady uniform flow, here conditions do not change with position in the stream or with time. Remember, for steady, the conditions do not change time, and uniform, the velocity is the same. So here, the condition do not change with the position in the stream or with the time. So they don't not change in the position in the stream, no time, there is no point, at any point the condition do not change, or they do not change also with time. They do not change with point and do not change with time. So for steady non-uniform, conditions change from point to point, but not with the time. So conditions change from point to point, but time. Reason being, steady time, but non-uniform, every point changes. So for you to have steady and uniform flow, they do not change with time. The conditions do not change with time, but they do change from point to point in the stream. Unsteady uniform, at this instant, at a given instant in conditions at every point are the same, but change with time. So here, conditions are the same from point to point, but they change with time. But here, conditions, but instead of an uniform flow, conditions change from point to point, but do not change with time. But here, they change with time, but they do not change from point to point. So just get the difference between the two. Unsteady and uniform, every condition now in the flow change from point to point and with the time at every point. Because here we have non-uniform, you expect the velocity is changing, the condition change, but now in unsteady non-uniform flow, every condition of the flow may change from point to point and with every time at every point. So just get the difference. The reason why we are doing this is you saw the topics. You can see steady flow. And here in steady flow, you'll find steady flow, steady non-uniform flow. You can see here steady flow in pipes, steady uniform flow, steady non-uniform flow. You can see here unsteady flows, steady, unsteady non-uniform, and also unsteady uniform flow. So with that, you'll be able to understand why we have got steady uniform flow, and we are saying the condition, the velocity is not changing. The conditions, the pressure, the velocity, and also cross-section area is not changing with time. Remember, when you are defining, when you yourself you are defining or you're in an exam, remember to name the conditions. Remember to name these three conditions: velocity, pressure, cross-section area. Because if you write conditions, do not, the conditions, one which condition do not change with time at a point, then it means I can add my own condition, temperature. So always name temperature, pressure, velocity, and cross-section area are the conditions that do not change with time, or they do change from one point to the other. So the other thing that we need to describe is in types of flows is laminar and turbulent flow. And in laminar and turbulent flow, this is because they are usually, they're the first one that we can determine. This because they are flows in real fluids. When you need to determine a flow, you start from laminar and turbulent flow. Then you can say that from there, the flow is uniform, this flow is non-uniform, things like that. But the first thing that you need to establish is laminar and turbulent flow. And laminar flow occurs at low speeds. The velocity is low. So when you have got low speeds, you expect you yourself to have a laminar flow. The velocity is low, so you expect very low, so expect. But at very high velocities, you expect the velocity to be turbulent. And for us to know if the flow is turbulent or the flow is laminar, we usually use an apparatus called Esbon-Reynolds. And that's why we have got something called Reynolds number. And Reynolds number is what determines that this flow is laminar, this flow is turbulent. Because for a turbulent flow, you don't expect it to be uniform flow. So we have to start from laminar, then you go to laminar and turbulent, so that we can be able to determine uniform flow, non-uniform flow, things like that. Because all of them are determined by the velocities, they are determined by areas, they are determined by pressures, all those, they are determined by the conditions. So here, we'll use the Esbon-Reynolds apparatus, and Reynolds apparatus, let me share another one. Something I needed to share, I can't see it. Yes, it's here. So Reynolds apparatus looks like this. Looks like this. You have dye in the container. Then with a certain velocity, you can be able to release it towards the valve. So there's a glass tube. I don't know if I can write somewhere here. I don't know how. Okay. I hope you can see my cursor. So here, so you release your dye. You have got water here. The water is for it to contain inside there, so that it can be able to fluctuate through the dye. You can be able to see through this glass tube here, so that using this glass tube you can see how the dye is flowing. So you have got a dye container, then the dye, then the water, then the glass tube, glass filament dye, which is here, and then you have got the valve here, itafungia maji siende. So if you open here at low velocities, the dye moves through this, through the water, through the glass tube at a very slow speed, and it moves through it. And this is how it looks when you have got laminar, a straight line for the laminar flow. You expect a straight line from the laminar flow. And also, we have got another flow that is in between. It's between laminar and turbulent. And between laminar and turbulent, the flow, I hope I'm still audible. So no one is saying anything. So between laminar and turbulent, we have something called transition. And transition, so that the flow can move from laminar to turbulent, there is that a phase of transition. Now it has moved from laminar, but it's not turbulent. So as the dye moves here, it's as you increase the speed, as you open this nozzle here, the speed increases of the flow, and it creates a wave-like filament of that dye filament, and that's what we call a transition. It's not laminar, it's not turbulent, it creates a transition. And the last one is when you increase that velocity, you can see you start with somewhere like a transition, and then the particles disperse all through. And when they disperse like this all through, we expect we have the turbulent flow. So with that, let me share again the notes. So with that, the diagram comes here. So the dye moves, and you can see the color, and you can see how the flow rate moves. The more you increase the flow rate, the more that you see. For the laminar, you have something like a straight line. And for the transition, which is in between, the transition is in between, you have a wave-like. But for turbulent, because it occurs at high velocities, you have them like that, moving like that. So that's the difference between the three. And you can see the kind of flow happens at high velocity. And this one is a transition between laminar and turbulent. But this one occurs at very low velocities. So with that apparatus, able to have and to see how the particles are behaving, how those dye particles are behaving, and they reach somewhere and they become erratic when they are in transition, when they are here on turbulent, and you can see every dispersion through that. So that's what the difference between laminar, transition, and turbulent. So on these three, how are you going to have them? Because you have said that we use Reynolds number. In Reynolds number, how are we? Because Reynolds number is represented by RE. So with this, how are we going to have this transition? How are we going to understand and get that we have the criteria? What is that criteria that we are going to use? And the criteria that we are going to use is a dimensionless group. You can see here. Naendelea kusoma zile vitu tunaenda kupatana nazo huko chini. A dimensionless group called Reynolds number. And Reynolds number is calculated by density times velocity times length divided by dynamic viscosity. Remember, there is a time we described dynamic viscosity and kinematic viscosity. So, and you remember we had, I think we did something to do with the Reynolds number, but I'm not sure. But also this L might change. This is because you can have a circular tube, and you only need to know what is on that with L as unit 1. So this one can change and become diameter. So it can be rho U D divided by mu, which is dynamic viscosity. But also we can have kinematic viscosity. And kinematic viscosity with a certain looks like a V is usually equal to mu over rho. Hapo mtanikumbusha. Is it mu over rho? So with that, you can have now, this one now transits and becomes UL over kinematic viscosity. Now this one becomes UL over kinematic viscosity. Or is it UL or rho UL? I think it's UL over kinematic viscosity. So that's how you can be able to transit that. And with this, on calculating the Reynolds number, now how do you determine from there? How do you determine that this one is laminar? And in this case, and in these calculations that we are going to deal with in the fluid mechanics too, we are going to use this, that Reynolds number, when it's less than 2000, it's laminar flow. But if it's between 2000 and 4000, then it's a transition flow. But if it's above 4000, then it's a turbulent flow. Remember, in some cases, and also in different studies, you find these numbers are varying. So in our fluid mechanics too, we are going to use this as our Reynolds number. That under 3000, when you use this formula and calculate and find the Reynolds number, maybe it's 1800. Remember, it's a laminar. If it's like 6700 and something, remember it's turbulent. If it's maybe 2800, remember becomes transition. With this, tutafanya maybe a short example, and then you'll see how we can be able to determine, and then they get the Reynolds number now in terms of kinematic viscosity, because the formula here is in dynamic viscosity. You can be able to derive that and get that. So with that, we are done with the first topic. And then now we have got our second topic, a very huge topic called momentum equations. So with that, maybe if you have got a question, I'll beg us to stop there, and we meet next week. So anyone with any question or anything you would like to say before